Welcome back to the first lecture of Organic Contaminants in the Subsurface. We started with a brief introduction of the mechanics of the course. We'll now carry on with some discussion of organic contaminants. We want to go over really two factors at the start. First of all is, what are the contaminants we're likely to find? And then how do we go about naming these contaminants? So what do we find in groundwater? Well, the major group of chemicals that we find in groundwater include petroleum hydrocarbons, which include additives to gasoline like MTBE or even ethanol. Another group of chemicals that's causing hydrogeologists a lot of concern are chlorinated solvents. Third group are pesticides and herbicides. These are a complex group of chemicals. We'll mention a few of them, but won't go into them in great detail in this course. A fourth group are coal tar, which contain PAHs, polynuclear aromatic hydrocarbons, and as well as other hydrocarbons. This list comes from Everton, who practices in Brazil, but it's the same list we'd come up with, I'm sure, from Canada or the US. Next problem is names. And we illustrate the problem here. A chemical called dioxane can also be called 1,4-dioxane, or it could be called 1,4-diethylene dioxide. So we can easily be confused by the different names. Chemical Abstract Service provides some clarity in that it assigns a number to each chemical. So if we know the CAS number, then we know the chemical for sure. We're often interested in what's in the chemical, so the molecular formula showing us the distribution of atoms is of some interest. One of our references, the Merck index, has a formula index, so if you know the formula, you can approach the name fairly directly. We're also interested in the reactions and behavior of these chemicals, and that's often illustrated by the molecular structure. In this case, this is dioxane. There's a number of chlorinated solvents that we have some interest in this course, and here's a list of them. The short forms are the ones we'll tend to use in the course, and they're the ones you'll see in the literature. Chlorinated solvents are often divided into ethenes, which contain a carbon-carbon double bond, ethanes, which contain a carbon-carbon single bond, and chlorinated methanes that just have one carbon. An interesting pair of chemicals is cis-1,2-dichloroethene, trans-1,2-DCE. These are two different compounds with significantly different chemical properties, and the structures are very similar. Cis has two chloride ions, or chloride atoms, on the same side of the carbon-carbon double bond. Trans has the two chlorides on opposite sides of the double bond. That subtle difference does make a significant difference in their behavior. Vinyl chloride's an important contaminant, very toxic. 1,1,1-trichloroethane and 1,1,2-trichloroethane, again, are slightly different in terms of how they position the chloride. In the 1,1,1 case, all the chlorides are associated with one carbon. In the 1,1,2 case, two are with one carbon and one is with the other. So these chemicals, the dichloroethanes, are isomers. It's probably the only isomers we'll deal with in the course, and they're just geometric isomers. That is, they have a very slight rearrangement of the molecules, and we get somewhat different properties. Aromatic hydrocarbons dominate our concern about petroleum hydrocarbons. The aromatic hydrocarbons are based on the benzene ring, which has three double bonds somewhere in that ring structure. It makes the ring very stable. In most contaminant situations, we're particularly concerned about the monoaromatic hydrocarbons, that is one benzene ring. And we often use the phrase BTEX, BTEX, for benzene, toluene, ethylbenzene, and the 3 possible xylene isomers, depending on where we put the second methyl group. There are more complicated monoaromatics, cumene, styrene, for example. PAHs are polynuclear aromatic hydrocarbons in which the benzene rings become fused or linked. Naphthalene is a very simple PAH with 2 benzene rings fused together. Biphenol has them joined by a bond. Anthracene has 3 rings. Benzoate-pyrene, a very toxic chemical, has 5 rings. And there are other ways to arrange the 5 rings, producing different chemicals. Another group of compounds that are derived essentially from the PAH structure are heterocycle compounds. Petroleum geologists often call these NSOs because they contain nitrogen, sulfur, or oxygen. A simple heterocycle compound, quinoline, has a nitrogen substituted for a carbon in the ring. Benzoate-pyrene has sulfur. Dibenzylfuran has an oxygen substitution. Carbazole is another nitrogen substituted compound. The interesting feature of these chemicals is we actually know less about their toxicity and probably have less experience with their environmental fate. But in general, these are more water soluble and more mobile in groundwater than the equivalent PAH. So, next lecture we'll talk about how these chemicals get distributed in the subsurface. Till then, bye for now.